Hello to everyone, I am Chiocca, a PhD student of Industrial Engineering at the University of Pisa. In this video, I present a part of my research project dealing with fatigue. Specifically, I will talk about the influence of residual stresses on the fatigue endurance of structural components. The presentation will cover both the numerical analysis and experimental tests. Generally speaking, residual stresses, in particular tensile residual stresses, are detrimental and degrading for the correct usability of a component. It can create several kinds of issues, for example, decreasing the buckling resistance, the fatigue life, or the static strength of a component, as well as creating stress, corrosion, cracking problems. In the following, two case studies will be presented, a welded joint and a notch specimen. In both cases, the effect of residual stresses on the fatigue life would be investigated. Specifically for the welded joint, both numerical models and experimental results will be presented. On the contrary, in the case of a notch specimen, only some experimental results are available up to now. I will focus now on the first case study, the tube-to-plate welded joint. The study specimen was obtained through MIG arc welding of a tube and a plate, both made of S355JR structural steel. The welding of relevance for our work is highlighted in this figure on the right. Fatigue tests were carried out by means of homemade test bench through two independent actuators. So we could create pure bending, pure torsion, or a mix of them. For this research project, we are dealing specifically with fully reversed pure torsion and pure bending loading. In order to study the effect of residual stresses, it was necessary to relieve some specimens. For this reason, a temperature of 630 degrees was maintained for 4 hours with subsequent cooling in the oven. Hardness and microstructure were analyzed to ensure correct treatment. In this graph, you can see the hardness curves around the weld seam region, both for DS welded and stress relief specimen. The hardness values were plotted over a normalized indentation length, the definition of which can be observed at the top left corner of this figure. As can be seen, the hardness decreases after the heat treatment and settles down to values traditionally expected for a stress relieving process of a structural steel. For the sake of clarity, only hardness measurements have been presented here. However, even from a microstructural point of view, differences were found due to the thermal process in a grain coarsening close to the weld seam region. Alongside the fatigue test, a numerical model was developed to determine the residual stresses that arise as a result of the welding process. The model uses an uncoupled thermostructural simulation, as you can see from the first two images, the thermal analysis and the structural analysis. This was followed by a material removal model to confirm the correctness of the results. Basically, results of relaxed strains around the weld seam were compared numerically and experimentally. These strains were experimentally measured using strain gauges and by incrementally drilling the specimen from the bottom of the plate after the welding process. To simulate the thermal load deriving from the welding process, a constant initial temperature method was implemented. The thermal process was initialized, activating a volume of elements at a starting temperature Ti, where Ti is only the parameter this method needs to work properly. The value of Ti was set for this particular case at 8500 Kelvin. This value has been obtained from the comparison of experimental and numerical temperature results by directly calculating temperature around the weld bead. Specifically, Ti does not represent the melting temperature of the base metal, but instead this is a fictitious parameter that incorporates all the assumptions that this model includes. The use of a constant initial temperature method in the thermal simulation poorly matched the classic approach of sequential activation of all the elements belonging to the element set. For this reason, a more representative simulation of the welding process from a structural point of view was implemented in this case. A correlation between element activation and element temperature is added. From the figure, it's possible to identify a sequential activation of the element with a temperature lower than the melting point. The result thus obtained represents what is expected from the solidification of a pool of molten metal during the welding process. Element's activation is gradual, even within the same section, and better describes the correct solidification of the material. The importance of using a three-dimensional numerical model is proven by the results of radial and residual stresses. These graphs show the stress behavior at the end of the welding process, specifically on the upper plate surface. The results of radial and stresses are shown starting from the weld toe here up to the end of the plate. It is clearly visible a drop in both radial and stresses near theta equal to 0, this angle here, where theta represents the run-in run-out point. This is precisely the area affected by the double thermal cycle, where the welding process begins and ends. It is worth noting that the values of stress, especially the radial one, are significant, with a value around 500 megapascal close to the weld top. This is because of the simplifying assumption of a null radius for the weld root and weld toe. The magnitude of residual stresses produced is quite considerable in this case. They indeed reach values around the yield strength of the material. Fatigue damage analysis was conducted numerically by means of a submodel analysis. A linear elastic model was firstly used to apply the correct sequence of loads and constraints, while the submodel with elastic plastic material behavior was used to obtain the structural values necessary for the calculation of damage factors. In red is highlighted the critical section of the submodel. In this section, the critical plane factors have been calculated. It was found that the weld root was a critical location for both loading conditions, so for pure bending and pure torsion. From a numerical point of view, residual stresses were mapped and initialized within the submodel. Both as welded and stress-relieved condition has in common the linear elastic and submodeling analysis. The only difference here lies in skipping the residual stress initialization phase with respect to the stress-relieved specimen. It should be noted that radii of the weld root and weld toes have been included in the submodel. Radii have been derived directly from investigating cross-sections of the weld seam. As the derived radius of the weld root is 0.2 mm, its presence has a negligible effect on the initialization phase for the residual stresses, even if this is done directly within the submodel. In the following, I will present experimental and numerical results for the two-to-plate welded joint. Experimental results from pure torsion fatigue tests are shown here, specifically for S-welded and stress-relieved specimens. The nominal stress range is shown over the number of cycles to break through. For the sake of clarity, the fat curve is also shown in order to have a comparison with standard. It can be seen that data related to relieved specimens seems to have a longer service life. This is also shown from the expected versus experimental number of cycles to break through, where the stress release data lay outside a factor 3 on the life range. It is worth noting that all points belonging to this graph, here at the top right corner, have been derived with reference to the fitting curve for torsion as welded data. Similarly, pure bending tests were carried out. Up to now, it was not found a significant difference between as-welded and stress-relieved specimens regarding the service life. In fact, as can be seen from the expected versus experimental number of cycles breakthrough, all stress-relieved data, together with the as-welded ones, fall within a factor 5 in the fatigue life range. So, what is presented here is the first numerical investigation where we tried to provide an answer to the different behavior between torsion and bending. First of all, damage was studied in the most critical point of the weld bead, in our case the weld root. The damage was calculated using critical plane factors. Here is shown Findley's critical plane factor over the nominal stress range for pure bending and torsional loading respectively. For the sake of simplicity, the maximum relative error between stress-relieved and as-welded conditions is also shown. It is evident that under similar loading conditions, the relieving process decreases the amount of damage more for the pure torsion than for the pure bending loading. One possible way of explaining the different behavior obtained in the two cases of torsion and bending was found in the hydrostatic stress. The pure torsional load does not provide, in fact, a counterblow for the hydrostatic stress, unlike the bending one. Therefore, we consider stress triaxiality as a damage factor. Four stress triaxiality factors are here presented, specifically for pure torsion and pure bending in S-welded and stress-welded conditions. As can be seen, in the absence of residual stresses and under pure torsional loading, the stress triaxiality is zero. On the other hand, if residual stresses are present, this will increase. In the case of bending, on the other hand, there is no great difference between S-welded and stress-welded condition. An explanation could be that during pure bending loading, in the presence of notches, cyclic plasticity stabilized the material and removed part of the initial residual stresses, leading to similar stress triaxiality values. I will present now an ongoing project that tries to reproduce the difference between pure bending load and pure torsional load in a more controllable environment. For this purpose, notched cylindrical specimens made from the same structural steel as the welded joints were investigated. By means of an axial torsion test bench, a 3-axis stress field can be established in notch. By controlling the axial preload, the magnitude of these stresses can be changed and different loading scenarios can be investigated. So the idea is to follow two different ways for doing the experimental test. In the first one, the test will be performed with a fixed preload that will be maintained during the fatigue test, while in the second one, the notch specimen will be compressed to locally go beyond the yield strength of the material in order to create residual tensile stresses in the region of the notch. In a similar way as for the welded joints, the aim here is to reproduce locally the stress state that is comparable to that produced in the weld seam, hence the choice of the notch specimen. This is in order to achieve the different behavior observed between torsion and bending that we saw before in the welded joint. From this graph, it can be seen how the equivalent plastic strain and the maximum normal stress varies as the preload changes. So we can in fact identify three main regions. The first one where the material remains in an elastic regime, the second one where there is a localized plasticity around the notch, and the last one where we have a generalized plasticity, so a nominal generalized plasticity in the notch region. In the following, I will present the first experimental results for pure torsion with a static preload of 10 kN, thus keeping the specimen in the elastic region. In these figures is visible a comparison of the failure surfaces for the notch specimen and the welded joint, both loaded in pure torsion. We can distinguish clearly the classic factory roof type fracture mode. Nominal shear stresses as a function of the number of cycles to failure is given in this slide. For this specific case, the end of the fatigue test has been imposed for a stiffness reduction of 20%. As expected, although the preload is quite low, this has worsened the fatigue life of the component, in a similar way as observed for a welded joint. Unfortunately, the number of data is still not sufficient for giving reliable scatter results. What will be done as a future development is trying to achieve the fatigue behavior found for the bending loaded welded joint and translate this also for these notch cylindrical specimens. To conclude, two case studies were described here. The first one is a welded tooth plate joint for which a numerical model was created specifically for the calculation of residual stresses deriving from the welding process. These stresses were then implemented in a numerical analysis for the calculation of fatigue damage factors. As a result, a difference was found between pure torsion and pure bending fatigue behavior. Recently, an experimental campaign on notch cylindrical specimens was started in order to better explain the causes behind the different behavior found for the welded joints. With cylindrical specimen, it is possible to better control the imposed stress field, thus eliminating the variability of the residual stresses resulting from the welding process. Thank you for your attention.